We can use the initial rate method to determine the rate constant and also the rate equation for a chemical reaction. So imagine we're given data about the rate during the very first part of a reaction. So we know that the concentrations of the various reactants are going to change as a function of time. But if we just look at the first, say, 1% of the course of a reaction, so it hasn't progressed very far, the concentrations haven't changed very much. And so we can see how that rate depends on those initial concentrations. You'll notice that this data is given in a way where we're emphasizing that these are the initial rates. These are the rates these are the initial concentrations, and this is the initial start. Okay, so that's why we call this the initial rate method. Okay, to do this, what you want to do is compare data where only one variable is changing. So if we look at this reaction, we've got three different experiments. So we could say we've got trial 1, trial 2, and trial 3. And we can see that between trial 1 and trial 2, we didn't change the concentration of hydroxide ion, but we doubled the concentration of ethyl bromide. And then we look at what happened to the rate. If we look at this rate's expressed in molarity per second, we can see that the rate doubled from 2.7 to 5.4 when we doubled the concentration of ethyl bromide. So there's a linear dependence. So if we doubled this, we doubled this. So we know that K times the concentration of ethyl bromide is going to be related to the rate in such a way that this exponent should be a 1. We normally wouldn't even bother writing it, but this shows that if we double this, we're going to double the reaction rate. And now we have to figure out what the concentration on hydroxide ion is. So we look for an experiment where we change the concentration of hydroxide ion, but not the concentration of ethyl bromide. So if we compare these two experiments, trial 1 and trial 3, we didn't change the concentration of ethyl bromide, but we did change the concentration of hydroxide. We doubled it. And if we look at the rate, we can see whether or not it affected, whether or not this change from here to here, let me mark that, this change from here to here, how did it affect these rates? Now, if it were zero order in hydroxide, we'd expect it to change the rate not at all. If it were first order, this doubling should lead this to double. If it's second order, then this doubling squared would be an increase by a factor of 4. And what do we see? We can see, oh, it just increased by a factor of 2. So this factor of 2 increased our rate by a factor of 2. So it's also first order in hydroxide. Okay, so this was true at the beginning of the reaction, but the rate law doesn't change during the reaction. So we can actually just write that at any time, the rate would be equal to K times the concentration of ethyl bromide times the concentration of hydroxide. This one was pretty easy to see what the exponents were by inspection. In some cases, the numbers might not come out so evenly, and it'll be a little harder. In that case, you should use the method I'm about to show you using a little bit of mathematics. So what we do, we pick any two trials where one variable changes. So let's start with these two trials. So we can see that only this variable is changing and not this variable. In this case, it was a nice even doubling, but this method I'm going to show you will work even if this increased by 30% or something like that. As long as one doesn't change and one does, the method will work. All right, so what we do is we'll label this trial 1 and trial 2, and then you write the rate equation divided by the rate equation. So you write, I'm going to write the rate for the second trial is equal to the rate constant times the concentration of hydroxide to the alpha, because remember we're imagining that we don't know the rate law yet. And then we've got the concentration of the ethyl bromide So at this point, we don't yet know what alpha and beta are. And the initial concentrations we're going to say are for this second trial. You can always divide an equation by an equation. So we'll divide by the first trial. So we've got K concentration of hydroxide to the alpha for the first trial, concentration of ethyl bromide for the second trial. Okay, so what's the advantage of dividing an equation by an equation? Well, anything that doesn't change will cancel out, and we'll get rid of some of the unknowns we have. So if we look at this, we can see first of all that the rate constant will be the same for both trials, so we can get rid of our rate constant. The V's are actually given here, so we don't have to worry about those. Those aren't unknowns. We don't know alpha and we don't know beta. We do know these initial concentrations for all the trials. So right now we have one equation and two unknowns. We can see in a second that alpha is going to cancel out because we can see that we chose trials where the concentration of hydroxide didn't change. In other words, we can say that the concentration of hydroxide in trial 1 was equal to the concentration of hydroxide in trial 2, because we're just looking at this set of trials here. So that means that we can cancel alpha, hydroxide to the alpha and hydroxide to the alpha because these numbers are the same and alpha is the same. So that cancels. Now we're down to just one unknown. So at that point, we can say that the ratio of reaction rates is just going to be the concentration of this reactant, the ethyl bromide, to the beta for trial 2 over the concentration of ethyl bromide for trial 1. We could just say it's this quotient taken to the exponent beta. Now we want to solve for beta in its exponents. There's a little trick you can use to isolate the beta, and that's to take the logarithm of both sides. So we've got the logarithm of V2 over V1 is equal to the logarithm of this whole quantity, which is concentration of ethyl bromide over concentration of ethyl bromide all to the beta. Okay, so we've taken the log of both sides. There we go. So let's write this out a little more neatly and see how we can somehow solve for that beta. Okay, great. So we have the log of the quotient of the rates is equal to the log of this expression where we have the quotient of the concentrations taken to the exponent beta. Now just to remind ourselves, we are dealing with this set of experiments here at trials 1 and 2 where all we changed was the concentration of ethyl bromide. So that's all that's going to affect the change in the rates. Great, so we want to solve for beta. To do that, we can use a little trick of logarithms that whenever you're taking the log of something to an exponent, you can take that exponent and just pop it in front like that. So we can rewrite this as the log of V2 over V1 is equal to beta times the logarithm of the ratio of those concentrations. So that was C2H5Br for the second trial divided by the concentration of ethyl bromide for the first trial. So now we can just solve for beta. So we get beta is equal to the log of V2 over V1 divided by the log of the ratio of the concentrations. So ethyl bromide for the second trial divided by ethyl bromide for the first trial. So when we plug in the numbers, we can see what this exponent is. Okay, so we've got our expression for beta, and so we can see that is equal to the log of a ratio of rates, and that is for V2 it is 5.4 divided by 2.7, and we have to check to make sure these exponents are the same. We can see that's going to cancel, right? So we can just write this as 5.4 divided by 2.7 divided by the log of the ratio of the concentrations, and for those same two experiments we've got 0.02 divided by 0.01. And so we can see this is the log of 2 divided by the log of 2. And of course, that's equal to 1. So beta is equal to 1. And if we go through a similar analysis, that was for, we just did for these experiments. If we do a similar analysis for experiments 1 and 3, we can see that what we're changing is the concentration of hydroxide and not of ethyl bromide. And we can end up getting what alpha is. And we'll see that if we do the same mathematics, we'll end up with alpha being equal to 1. So the last step, now that we have a rate equation, that we know that it's first order in hydroxide and first order in ethyl bromide, is to come up with a numerical value for the rate constant. Okay, so it's first order in ethyl bromide, first order in hydroxide. What's the value for the rate constant? So we just divide the rate by the rest of the rate law, which in this case is just hydroxide concentration to the first and ethyl bromide concentration to the first. So we plug in those numbers, and we have to pick any one of these. And since the rate equation is true for any one of the trials, we could just pick any of them and it will work out. So we've got the rate was 2.7, 10 to the negative fifth. That's molarity per second. And then we have the concentration of hydroxide, it's 0.1 molar. Concentration of ethyl bromide is 0.01 molar. We can get our value for K. And so we can see that in this case, it's going to be 2.7 times 10 to the negative 2. So we had molarity per second divided by molarity squared. And so we can see this is going to give us inverse seconds, inverse molarity. And to avoid confusing the symbol for molarity with mega as a prefix, we usually just write that out as moles per liter. So we'd say 2.7 times the negative 2, and that would be inverse seconds, inverse moles over liters. And that is our rate constant. And as a check, you could just verify that that would come out the same for any of the other remaining trials. And if it does for all of them, you've got the right rate equation.